Today, I want you to imagine something with me. Picture yourself building an intelligent system, not just a simple algorithm, but a fully functional tool, something that truly works in the real world. Many of us, when we think of machine learning, we tend to focus only on those fascinating algorithms. But a successful ML system, well, that involves a far more comprehensive journey, a pipeline that goes from the initial spark of an idea all the way to a system humming along in production.
Oh, absolutely. It's an entire ecosystem, really. So many moving parts beyond just the model itself.
And that's really our mission today. This deep dive is your curated guide through that entire end-to-end machine learning project. We've pulled together insights from a rich collection of practical, hands-on source material, and we're aiming to deliver those surprising nuggets of knowledge you might not find in a standard textbook. We're going to unpack the key phases, those surprising insights, and the essential tools that can empower you to take an ML project from conception right through to successful deployment and maintenance. Our goal is simple: to give you a clear roadmap, sort of demystify the process, and highlight the why behind each critical step.
Yeah, we'll start by looking at how ML fundamentally shifts how we even approach problem solving. Then we'll get into the really practical steps: acquiring data, exploring it, getting it ready. We'll cover how models truly learn and improve, what goes into building some of the most cutting-edge AI systems out there. And finally, how to actually get these systems working reliably in the real world and, just as importantly, keep them running smoothly over time.
All right, let's unpack this then. We hear machine learning all the time, but at its core, how is it fundamentally different from, say, traditional programming, where you'd explicitly write rules for every single scenario?
Well, the fundamental shift is that ML is about making machines learn from data, rather than being explicitly programmed for every single outcome. Think about a spam filter. A traditional approach would involve a programmer writing this massive, complex, maybe endless list of rules. If the email contains Nigerian prince and either urgent money, then mark it as spam. That gets incredibly difficult to maintain as spammers get smarter, right?
Right, new tactics constantly emerge, and that's where ML truly shines, I suppose.
Precisely. An ML-based spam filter learns automatically which words and phrases are strong predictors of spam. It does this by detecting frequent patterns in loads of examples of spam versus legitimate emails. The really profound insight here is that the ML solution adapts dynamically. It's often described as much shorter, easier to maintain, and most likely more accurate. Precisely because it doesn't need constant manual rule updates. It learns and evolves as the spam itself evolves.
That adaptability really seems key. It's why ML excels in problems that are just too complex for traditional programming. We've seen this pretty dramatically in areas like game playing, haven't we? Thinking about DeepMind's AlphaGo program.
Exactly. AlphaGo didn't have rules programmed for every single possible move in Go. That would be impossible. Instead, it learned its winning strategy by analyzing millions of games and then, crucially, playing against itself countless times. It eventually beat the world champion. That's reinforcement learning and action learning through trial and error, basically, by interacting with an environment and getting feedback.
Okay, so that leads us into the main categories of ML systems. You mentioned reinforcement learning. What are the others?
Right, so there are basically three main categories. First, you have supervised learning. This is probably the most common type. It's where the system learns from labeled training data to make predictions. So if you have historical data with clear inputs and corresponding outputs, like housing features matched with actual sale prices, or emails already labeled as spam or not spam, that's supervised learning, it's used for regression or classification tasks.
Labeled data is the key there. So what if you don't have labels?
That's where unsupervised learning comes in. Here, the system has to find patterns in unlabeled data all by itself. It's kind of like throwing a big pile of data at the system and asking, what interesting structures or groups or anomalies can you find in here? This covers tasks like clustering customers into different segments based on their behavior, or detecting unusual activity on a network that might signal an intrusion.
Okay, and the third was reinforcement learning, like AlphaGo.
Exactly. Agents learn through interaction with an environment, receiving rewards for good actions and penalties for bad ones. They essentially learn the best strategy, the optimal behavior, without explicit instructions on how to do it.
So before you even think about code or algorithms, our sources really hammer home one absolutely crucial first step. What is it, and why is it so vital before getting bogged down in the technical stuff?
It really is about stepping back and looking at the big picture first. You absolutely have to understand the problem inside and out. Like, take the housing price example. Are you trying to predict the exact dollar amount? Or maybe just broad categories like expensive, mid-range, affordable. Your choice there completely changes the kind of model you'll need and how you evaluate it.
So understanding the objective. What else is part of that big picture?
You also need to select a clear, measurable performance metric right at the start. Something like root mean square error, or RMSE, is common for regression problems where you're predicting a number. And, this is critical, you must consult with field experts or the client team. They have the domain knowledge, they can help you verify your assumptions, clarify the actual requirements, and crucially, prevent you from building a technically brilliant solution to the wrong problem.
Okay, makes sense. Frame the problem, define success, talk to the experts. So you've done that. Now it's time to actually get your hands dirty with the data, the real raw material of machine learning. What's the first practical step here?
Well, data acquisition. Simple as that sometimes. For instance, with the popular California housing dataset example, it just means downloading the data file. And then using a tool Pandas is super common in Python to load it into your workspace, like into a data frame. This is where your journey with the actual data begins.
And once you have it loaded, you can't just jump straight into building a model, right? You need to get a feel for it first.
Absolutely not. Initial data exploration is vital. You need to understand what you're actually working with. You can use simple methods like value counts in Pandas to see the different categories in a feature and how often they appear, like for ocean proximity, how many houses are near the bay versus inland. Or use Describe to get a quick statistical summary of all the numerical attributes mean, standard deviation, minimum, maximum, those quartiles. It helps you grasp the distributions and spot potential issues early on.
And speaking of issues, the sources mention these common data quirks you might find, like values being capped. They use housing median age and median house value as examples. What does capped mean here, and why is it a problem?
Capped means the values stop at a certain threshold. For example, the median house value in that dataset might be capped at $500,000. Any house worth more is just recorded as $500,000. This is a potentially serious problem if your client needs precise predictions beyond that cap. Your model literally can't learn to predict higher values because it never sees them in the training data.
I see. So the data itself has limitations.
Exactly. The core insight really is that data might only tell you part of the story, or even a misleading one, if you don't understand its origins and limitations. You have to discuss these quirks with your client or the domain experts. Ignoring them can lead to models that seem okay in testing but perform poorly, or give nonsensical predictions in the real world.
Okay, this next point seems really fundamental. Our sources highlight this as maybe the critical aha moment in practical ML, creating your test set early on. And then the absolute cardinal rule, never ever look at it. Why is this discipline so non-negotiable? Why is our own brain, normally our best asset, kind of our worst enemy here?
This is absolutely paramount. It's all about avoiding something called data snooping bias. Think of it this way. Your brain is an incredible pattern detection machine. That's usually great, but here it makes it highly prone to overfitting. If you even glance at that test set data while you're developing your model, maybe tweaking features, trying different algorithms, you will subconsciously start making choices that perform well on that specific set of data. You'll end up with a performance estimate that's way too optimistic.
So you're essentially tuning your model to the test set without realizing it.
Exactly. The real insight here is that human bias, our own pattern matching ability, is the first and maybe most insidious threat to your model's real-world performance. You absolutely have to protect the integrity of your final evaluation by keeping that test set completely untouched, pristine, until the very end when you have your final chosen model ready for one last check.
So create it, lock it away, forget about it. Got it. But how do you make sure that this test set you've locked away is actually representative of the overall data? You don't want it to be accidentally skewed, right?
Yeah, that's a great point. You use techniques like stratified sampling. For example, in the housing data set, median income is known to be a very important predictor of price. So you might first create income categories, grouping the continuous income data into discrete bins. Then you use a tool like scikit-learn's stratified shuffle split. It ensures that your test set and your training set has the same proportion of samples from each income category as the original full data set. This prevents you from accidentally getting, say, mostly high-income examples in your test set, which would give you a misleading evaluation. It ensures balance.
Okay, so stratified sampling for representativeness. Now you've got your training data, your sacred test set is locked away. Time for data preparation strategies. What are some of the key steps involved here?
Right, now you work only with the training set. First up is often handling missing values. Real-world data is messy. You might use something like scikit-learn's Simplimputer to fill in missing numerical data. maybe using the median value of that feature, which is often more robust to outliers than the mean.
What about non-numerical data, like text categories?
For categorical features text labels like inland or 1H ocean, you need to convert them into numbers that the model can understand. A very common technique is one-hot encoding. This creates a new binary 0 or 1 feature for each category. So if you have 5 ocean proximity categories, you get 5 new features.
But what if you have a lot of categories, like, say, zip codes or job titles?
Yeah.
Wouldn't one-hot encoding create way too many features?
Yes, that's a huge problem called the curse of dimensionality. If an attribute has thousands of categories, one-hot encoding becomes impractical. It massively increases the number of input features, making the model slow and potentially harder to train. In those cases, you might try replacing the categorical feature with useful numerical features derived from it, maybe like calculating the distance to the ocean instead of using the ocean proximity category directly. Or a more advanced and often very powerful technique is to use embeddings.
Embeddings, what are those?
Think of embeddings as a learned, dense numerical representations for each category. Instead of a sparse vector with mostly zeros like one-hot, you get a shorter vector of continuous numbers. The amazing thing is that the model learns these representations during training, and similar categories often end up with similar embedding vectors. It captures semantic meaning. So the model can understand that, say, software engineer is perhaps more similar to data scientists than to chef, something one-hot encoding completely misses. It's incredibly powerful for high cardinality features.
Fascinating. Okay, what else in preparation?
Numerical scaling is almost always necessary. Machine learning algorithms often perform poorly if the input numerical features have very different scales, like one feature ranges from 0 to 1, and another ranges from 0 to 1 milzinhar. The algorithm might unfairly weight the feature with the larger values, so you use techniques like standardization, using scikit-learn standard scaler to rescale features so they all have roughly comparable ranges, typically 0 mean and unit variance.
And I remember reading about experimenting with attribute combinations. This sounds less like a standard procedure and more like creative feature engineering.
It absolutely is. It's often where a lot of the predictive power can be unlocked, and it requires some domain knowledge or just insightful exploration. You might try creating new features by combining existing ones. For instance, in the housing data, calculating rooms per household, total rooms divided by number of households in a district, or bedrooms per room. Sometimes these combined features reveal hidden correlations or patterns that weren't obvious in the original raw data. The sources note that median income turns out to be the #1 predictor of housing prices, but these engineered features can sometimes capture other important nuances.
Right, adding that domain knowledge or intuition, and to manage all these different transformation steps, imputation, encoding, scaling, maybe combination in an organized way.
That's where pipelines come in. Sklearn.pipeline. Pipeline is an incredibly useful tool. It allows you to chain together multiple transformation steps into a single object. You define the sequence. First impute missing values, then scale numerical features, then encode categoricals, etc. This makes your workflow much cleaner, ensures you apply the steps in the right order, prevents data leakage between steps, like fitting a scalar on the full dataset before splitting, and makes it super easy to try out different combinations of pre-processing steps. It's essential for robust and reproducible ML.
Okay, data prepped, pipelines built. We finally get to the core, selecting and training the actual model. The sources suggest starting simple, but sometimes that's, well, too simple.
That's right. It's often good practice to start with a simple model, like linear regression, as a baseline. But it might underfit the training data. Underfitting means the model is too simple to capture the underlying structure of the data. Your training error and your validation error will both be high. This might indicate that your features don't provide enough information, or maybe the linear model itself just isn't powerful enough to model the potentially complex nonlinear relationships in the data.
So if linear regression underfits, you need something more powerful.
Yeah.
Like a decision regressor, perhaps.
Exactly. A model like decision-free regressor is much more flexible. It can learn complex, nonlinear decision boundaries by recursively splitting the data based on feature values. It's capable of fitting the training data much more closely.
But fitting the training data closely isn't the whole story, is it? We need to evaluate performance rigorously. And the sources warn that simple accuracy, especially for classification, can be really misleading.
Hugely misleading. Think about a medical diagnosis test where only, say, 1% of patients have a rare disease. A model that always predicts no disease will achieve 99% accuracy. But it's completely useless, right? It misses every single actual case. So especially for classification, you need more nuanced metrics.
Okay, what are the key ones we should be looking at?
For classification, we often focus on precision and recall. They capture different aspects of performance, and there's usually a trade-off. Precision answers the question. Of all the instances the classifier predicted as positive, for e.g. spam, how many were actually positive? High precision means few false positives. Recall, on the other hand, answers. Of all the instances that were actually positive, how many did the classifier correctly identify? High recall means few false negatives.
And the right balance depends on the specific problem.
Totally depends on the context. Think about filtering videos to ensure they're safe for kids. You'd want extremely high precision. You'd rather mistakenly block a few safe videos, lower recall, than let even one unsafe video through, avoid false negatives at all costs. But contrast that with, say, detecting shoplifters in a store via security cameras. Maybe you'd accept lower precision, more false alarms for security to check, in order to achieve higher recall, catching most of the actual shoplifters.
So as a trade-off, is there a metric that combines them?
Yes, the F1 score is the harmonic mean of precision and recall. It gives a single number, and it tends to be high only if both precision and recall are reasonably high. It's useful when you need a balance. Then there's the ROC curve receiver operating characteristic. It plots the true positive rate, which is just recall, against the false positive rate at various decision thresholds. The area under this curve, the AUC, gives you a single metric to compare classifiers. A perfect classifier has an AUC of 1, while random guessing gives 0.5.
Okay, ROC and AUC.
Uh-huh.
But the sources also mention a rule of thumb about when not to rely solely on ROC.
Right. The general rule of thumb is to prefer the precision recall PR curve over the ROC curve when the positive class is rare, like the disease example, or when you care more about false positives than false negatives. The PR curve gives a more informative picture in those imbalanced scenarios.
Okay, this brings us squarely to what you call the core challenge of machine learning. The bias variance trade-off, and specifically, the massive problem of overfitting. The model does brilliantly on the data it trained on, but it just doesn't generalize. It fails when it sees new, unseen data. It's like that student who memorized the textbook answers perfectly but couldn't solve a new problem on the exam. Can you maybe share a real-world example where this overfitting trap had significant consequences?
Oh, absolutely. That analogy is spot on. I've seen it countless times, especially, say, in financial modeling. You build a model to predict stock movements based on historical data. It looks amazing on the past data, captures every little wiggle. You think you found the holy grail, but then you deploy it in the live market, and conditions change just slightly, and the model completely falls apart because it had essentially memorized the noise and specific quirks of the past data rather than learning the true underlying generalizable patterns. It didn't understand the why. That's overfitting.
A costly mistake in finance, I imagine. So how do we fight this? What are the main techniques?
Overfitting really is the central challenge. One major set of techniques is regularization. This involves adding a penalty term to the model's cost function during training, discouraging it from learning overly complex patterns or relying too heavily on any single feature. Common types include RID regression, L2 penalty, lasso regression, L1 penalty, and elastic net, a combination of both. They effectively constrain the model's parameters, forcing them to be smaller. Lasso is particularly interesting because its L1 penalty tends to shrink some feature weights all the way down to 0, effectively performing feature selection and creating sparse models that use only a subset of the most important features.
And the amount of this regularization is controlled by something called a hyperparameter, right?
Exactly. Hyperparameters are parameters that are not learned from the data directly. They are settings for the learning algorithm itself, like the strength of the regularization penalty. You have to choose them before training starts. Another really powerful technique, especially vital for deep neural networks, is early stopping.
Early stopping. How does that work?
It's quite intuitive. While training your model, you periodically evaluate its performance not just on the training data, but on a separate validation set, data held out from training but not the final test set. Typically, the error on both training and validation sets will decrease initially, but at some point, the training error might continue to decrease while the validation error starts to increase. That's the point where the model is starting to overfit. Early stopping simply means you stop the training process right there when the validation performance is at its best and save that version of the model. It prevents the model from chasing perfection on the training data at the expense of generalization.
Makes sense. Stop before you memorize too much. And you mentioned hyperparameters like the regularization strike. Finding the best values for these seems crucial. How is that done?
That's hyperparameter tuning. Since these aren't learned during normal training, you have to systematically search for the best combination. Techniques like grid search, trying all combinations in a predefined grid, or randomized search, sampling random combinations, are common. You typically use cross-validation during this process. Cross-validation involves splitting your training data into multiple folds, training the model on some folds and validating on the remaining one, and repeating this process so each fold gets used for validation. This gives a more robust estimate of how a particular set of hyperparameters will perform on unseen data, helping you select the best overall model configuration before that final check on the test set.
Right. Okay. So we've optimized our models, regularized them, tuned hyperparameters, ensuring they generalize well. But what happens when the problems we're tackling are just incredibly complex, when even these sophisticated techniques aren't quite enough? That feels like the doorway into deep learning, the engine behind so many of the advanced AI systems capturing headlines today.
It really is a significant leap in capability for certain kinds of problems. At the heart of deep learning are artificial neural networks, or ANNs. Now, the initial idea was loosely inspired by biological neurons, leading to early models like the perceptron. But the real power came with stacking layers of these artificial neurons into multi-layer perceptrons, or MLPs. These are essentially stacks of fully connected layers, and they turn out to be universal function approximators, highly effective for both classification and regression on complex data.
And inside these networks, these layers, there are components called activation functions. What role do they play?
They're absolutely critical. Activation functions introduce nonlinearity into the network. Without them, even a deep stack of layers would just behave like a single linear model. Common ones include the rectified linear unit, or ReLU. It's computationally very efficient and works surprisingly well in practice. There are more advanced ones too, like SCLU, Scaled Exponential Linear Unit, which has properties that can lead to self-normalization within the network. This is really helpful for very deep networks because it can automatically combat the tricky vanishing or exploding gradients problem.
Vanishing or exploding gradients. Sounds dramatic.
It is. It's when the error signals being passed backward through the network during training become either incredibly tiny, vanish, or astronomically large, explode, as they propagate through many layers. This effectively stops the earlier layers from learning properly. Techniques like careful initialization, batch normalization, and activations like SCLU are designed to mitigate this, allowing us to train much deeper networks effectively.
And building these complex networks, which used to be quite daunting, has become much more accessible thanks to libraries like Keras, especially now that it's integrated into TensorFlow as TF.Keras.
Oh, absolutely. TF.Keras has been a game changer for usability. It provides these really user-friendly APIs for building models. There's the sequential API for simple stacks of layers, the functional API for more complex architectures with multiple inputs or outputs or shared layers, and even the subclassing API for maximum flexibility if you need to build something really custom. Plus, it provides straightforward methods like fit to handle the training loop, evaluate to check performance, and predict to get outputs from new data.
And it has helpful tools for managing the training process, too.
Yeah, callbacks are super useful. You can add things like model checkpoint, which automatically saves your model during training, maybe only saving the version that achieved the best performance on the validation set so far. And TensorBoard integration lets you visualize your training progress in real time. You can track loss curves, metrics, visualize the network graph, even look at activation histograms. It's invaluable for understanding what's going on and for debugging or optimizing your training.
Okay, so we have the basics of ANNs and Keras, but deep learning really shines with specialized architectures designed for specific types of data, right?
Yeah.
Let's start with convolutional neural networks, CNNs, which have completely transformed computer vision.
CNNs are just brilliant for image processing. Their core idea is that patterns like edges, textures, shapes are important regardless of where they appear in an image. They achieve this using specialized layers. Convolutional layers apply learnable filters across the image, acting like detectors for specific features. Each filter slides across the input, creating a feature map that highlights where that feature occurs. Then you often have pooling layers, like max pooling, which downsample the feature maps, making the representation more compact and robust to small variations in the feature's position.
And these layers working together are what led to those huge leaps in image recognition accuracy.
Precisely. Stacking these convolutional and pooling layers allows the network to learn a hierarchy of features, simple edges in early layers, combine into textures and parts of objects in middle layers, and then into complete objects in later layers. This architecture led to those dramatic improvements in challenges like the ImageNet competition, where the top 5 error rate plummeted from around 26% down to an incredible 2.3% in just about 6 years, largely thanks to deeper and more sophisticated CNNs.
That's staggering progress. And a key practical aspect here is transfer learning.
Yes, transfer learning is hugely important in practice, especially with CNNs. Training a state-of-the-art image model from scratch requires massive data sets, like ImageNet with over 1 million images, and immense computational resources. Instead, you can take a pre-trained model like ResNet, VGG, or Exception that has already been trained on ImageNet. You can then reuse its lower layers, which have learned general visual features like edges and textures, and just replace or fine-tune the top layers for your specific task, e.g. classifying breeds of dogs instead of the 1,000 ImageNet categories. This significantly speeds up training, requires much less labeled data for your specific problem, and often leads to better performance than training from scratch. It's the standard approach for many computer vision tasks now.
Makes sense. Leverage the knowledge learned from vast data sets, okay, from images to sequences. What about data where order matters, like text or time series? That's where recurrent neural networks, RNNs, come in.
Exactly. RNNs are designed specifically for sequential data. Unlike standard feed-forward networks like MLPs or CNNs that process fixed-size inputs independently, RNNs have connections that loop back on themselves. This creates a kind of memory, allowing the network's output at a given time step to be influenced by previous inputs in the sequence. This makes them suitable for tasks where context and order are crucial.
What kind of applications are we talking about?
All sorts. Forecasting time series, predicting future stock prices, website traffic, or weather patterns based on past data. Natural language processing is a huge area, things like sentiment analysis, machine translation, and even text generation. You might train a character-level RNN on, say, all of Shakespeare's works, and then have it generate new text that mimics his style.
But early RNNs had some limitations, right, particularly with longer sequences.
They did. The simple RNN architecture struggled with the same vanishing exploding gradient problem we discussed earlier, especially over long sequences. This made it difficult for them to capture long-range dependencies in the data, like connecting a pronoun near the end of a long sentence back to the subject mentioned at the beginning. Their memory was effectively quite short-term. This led to the development of more sophisticated recurrent units like LSTM, long short-term memory, and GRU, gated recurrent unit cells.
LSTM and GRU, what makes them better?
They have internal mechanisms called gates. Think of them like little controllers within the cell. These gates learn to regulate the flow of information, deciding what information to store in the cell's memory state, what to forget, and what to output at each time step. This allows them to selectively remember relevant information over much longer periods and forget irrelevant details, overcoming the short-term memory limitations of simple RNNs and making them much more effective for complex sequence tasks.
Okay, so LSTMs and GRUs improved memory. But then came another revolution, particularly in natural language translation, involving attention mechanisms and the transformer architecture. These seem to be the foundation for the incredibly powerful language models we see now, like GPT and BERT.
They absolutely are. Attention mechanisms were a huge breakthrough, initially applied to neural machine translation, NMT. Before attention, sequence-to-sequence models, often using LSTMs, had to compress the entire meaning of the input sentence into a single fixed-size context vector, which then had to be decoded into the target language. This became a bottleneck, especially for long sentences. Information got lost.
So how did attention help?
Attention mechanisms allow the decoder, as it generates each word in the translation, to look back and pay attention to specific relevant parts of the input sentence. So, when translating the French word le chat to English as it generates the, it might focus on le, and as it generates cat, it strongly focuses on chat. It learns alignment between input and output words. This significantly improved translation quality, especially for longer sentences, because the model wasn't forced to rely solely on that single compressed context vector.
And the transformer architecture took this even further.
It did. The seminal paper, Attention is All You Need, introduced the transformer architecture. Its key innovation was relying entirely on attention mechanisms, specifically a mechanism called multi-head self-attention, and completely ditching the recurrent connections of RNS LSTMs. This had a massive advantage. Because there were no sequential dependencies in the network architecture itself, attention can look at all input words simultaneously, it could be parallelized much more effectively during training, allowing researchers to train vastly larger models on much more data than was feasible with RNNs. This architecture, with its self-attention allowing the model to weigh the importance of different words within the input sequence itself, proved incredibly powerful for understanding context and nuance in language. It's the foundation for models like BERT, GPT-2, GPT-3, and subsequent large language models that excel at understanding and generating human-like text.
Incredible. Parallelization enabling scale. Okay, one more area within deep learning.
Yeah.
Generative models. These are the ones that can actually create new data, right? Like autoencoders and GANs.
Yes, generative models are fascinating because they learn the underlying distribution of the training data and can then sample from that distribution to create entirely new examples. Autoencoders are one type. They're unsupervised networks typically used for dimensionality reduction or feature learning. An autoencoder consists of an encoder that compresses the input data into a low-dimensional latent representation, or coding, and a decoder that tries to reconstruct the original input from this compressed representation. By forcing the data through this bottleneck, the network learns a dense, meaningful representation of the input. They can be used for things like visualizing high-dimensional data, like the fashion MNIST dataset images, in 2D or 3D space by plotting their latent codes, or for anomaly detection.
And variational autoencoders.
Variational autoencoders, or VAEs, are a more sophisticated, probabilistic take on autoencoders. Instead of just learning a single coding, they learn the parameters of a probability distribution, like a mean and variance, in the latent space. This makes them truly generative. You can sample a random point from this learned latent distribution and feed it to the decoder to generate a completely new data instance that looks like it could have come from the original dataset.
Cool. And the other big name in generative models is GAN's generative adversarial networks. These sound intriguing, like two networks battling it out.
That's a perfect way to describe it. A GAN consists of two neural networks trained simultaneously, a generator and a discriminator. The generator's goal is to create fake data, VRD images, that looks completely realistic, starting from random noise. The discriminator's goal is to look at an instance, either a real one from the training set or a fake one from the generator, and decide whether it's real or fake. They have opposing objectives, hence the adversarial name. The generator tries to fool the discriminator, and the discriminator tries to get better at catching the fakes.
And this competition makes them both better.
Exactly. As they train together, the discriminator gets better at spotting fakes, forcing the generator to produce increasingly realistic outputs to try and fool it. This adversarial process can lead to the generation of stunningly convincing new data. Our sources mention architectures like DC-GANs, deep convolutional GANs, that became famous for generating highly realistic images of faces. They even demonstrated performing arithmetic on faces in latent space.
Arithmetic on faces. What does that even mean?
It's wild. The latent space is that compressed representation the generator learns internally. It turns out this space often captures high-level semantic features of the data. So researchers found they could take the latent vector for an image of a man with glasses, subtract the vector for a man without glasses, add the vector for a woman without glasses, and the resulting vector, when fed to the generator, would produce an image of a woman with glasses. It shows the GAN didn't just memorize pixels, it learned abstract concepts like glassness and gender, and could manipulate them in this learned latent space. Truly profound.
Mind-bending stuff. Okay, so whether it's a complex deep model or a simpler one, you've trained it, tuned it, you're happy with its performance on your validation set, what's next? Getting it out of the lab and into the real world. Deployment, monitoring, and scaling. This sounds like it's more than just clicking a launch button.
Oh, definitely. It's a whole critical process in itself, moving from a research prototype to a production system. First, you really need to make your solution production ready. That means cleaning up your code, making it robust and efficient. It means writing comprehensive documentation so others or your future self can understand it. It means creating solid tests, unit tests, integration tests, and crucially, you need to save your final trained model, and this should include the entire pipeline, the pre-processing steps, as well as the model itself in a reliable, standardized format. TensorFlow's saved model format is designed for this. It packages everything needed for inference.
And once it's saved and packaged, how do these models typically get used in a larger system?
Very often, they're wrapped in a web service, usually using a REST API or maybe gRPC. This means other parts of your company's infrastructure or maybe external applications can simply send a request with input data to an endpoint, and the service hosting your model will return the prediction. This approach provides great flexibility, it helps with scalability, and it keeps the model nicely decoupled from the applications that use it.
Makes sense. But the world keeps changing, right? The data your model sees in production today might be different from the data it was trained on months ago. Models can't just be deployed and forgotten, can they?
Absolutely not. That's a recipe for disaster. Monitoring and maintenance are utterly crucial for any deployed ML system. You have to actively monitor your model's live performance. And importantly, this often isn't just about technical metrics like prediction latency or error rates. You need to track downstream business metrics that the model influences. For instance, if your model recommends products, are people actually buying those recommended products? If that conversion rate starts dropping over time, your model might be the culprit. Its predictions might be becoming less relevant.
Why would its performance degrade?
This often happens because the underlying data patterns change over time, a phenomenon sometimes called data drift or concept drift. Customer preferences change, fraud patterns evolve, the world moves on. Your model, trained on older data, gradually becomes stale. That's why regularly retraining your models on fresh, recent data is absolutely essential. You need a process to automatically collect new data, retrain, evaluate, and potentially redeploy updated versions of your model to prevent this performance degradation and ensure it stays relevant and effective.
So, continuous monitoring and retraining. What if your service becomes really popular? You're suddenly getting thousands, maybe millions of requests per second. How do you handle that scale?
Yeah, scaling is a critical consideration for production ML. That's where dedicated model serving solutions really shine. TF serving, TensorFlow serving is a great example. It's a high-performance serving system specifically designed for deploying ML models in production. It handles things very efficiently, like loading models, handling concurrent requests. It supports crucial features like model versioning. You can deploy multiple versions of a model simultaneously, maybe route a small percentage of traffic to a new version for testing, A/B testing or canary releases. It allows for graceful transitions between versions so you can update your model without any service downtime. And it has neat tricks like automatic batching.
Automatic batching, how does that help?
GPUs, which are often used to accelerate predictions, perform much better when they process data in batches rather than one instance at a time. TF serving can automatically collect multiple individual inference requests that arrive close together and batch them up before sending them to the GPU. This significantly improves throughput and hardware utilization, allowing you to serve more requests per second with the same hardware.
Very cool. And what about deploying models not to big servers, but to, say, mobile phones or even smaller devices, or directly in a web browser?
Yeah, that's becoming increasingly common for on-device AI or privacy-preserving applications. For deploying models onto mobile, Android OS, or embedded devices like microcontrollers, there's T-Flight, TensorFlow Lite. It provides tools to convert your regular TensorFlow models into a lightweight format, optimized for low latency, small binary size, and reduced power consumption. And for running models directly within a web browser using JavaScript, there's TensorFlow.js. This allows you to build interactive ML applications that run entirely on the client side, which can be great for real-time feedback or when you don't want user data leaving their device.
So specialized tools for different deployment targets. Finally, let's touch on leveraging the hardware itself, especially during training. GPUs have obviously been a massive accelerator for deep learning.
They've been absolutely fundamental. The highly parallel nature of GPUs having thousands of simple cores is perfectly suited for the types of computations common in deep learning, especially large matrix multiplications and convolutions. Training complex models on large datasets can take days or even weeks on CPUs, but GPUs can often reduce that time dramatically, sometimes by orders of magnitude, making experimentation and iteration much faster.
And what if one GPU isn't enough? Can you train across multiple GPUs?
Yes, and TensorFlow makes this surprisingly straightforward with its distribution strategies API. For training on multiple GPUs within a single machine, the mirrored strategy is commonly used. With just a few lines of code added to your standard Keras training script, it automatically replicates your model across all available GPUs. During training, each GPU processes a slice of the input data batch in parallel, and the gradients are efficiently aggregated and applied to update the model parameters across all replicas. This can provide near-linear speedups in training time, allowing you to tackle much larger models or datasets than would be feasible on a single GPU. It really democratizes large-scale training to some extent.
Wow. Okay. We have genuinely covered a massive amount of ground today. It feels like a complete journey. We started right at the beginning. defining what an ML problem really is, how that mindset shifts problem solving. We dove deep into the practicalities of getting data, the rigorous cleaning and preparation needed, then navigating the world of training from simple regressions, understanding trade-offs like bias and variance, tackling overfitting, all the way up to the powerhouses of deep learning, CNNs, RNNs, transformers, even generative models like GANs. And then, crucially, we brought it all back to the real world, deploying these systems, the vital importance of monitoring them, maintaining them, and scaling them effectively using tools like TF serving and distributed training.
It really is an end-to-end process, isn't it? And understanding that entire pipeline, not just focusing on the flashy algorithm part, is so incredibly valuable. I think the real power of machine learning, the real potential, isn't just unlocked by knowing the theory of the algorithms, but by mastering this whole practical journey that turns raw data into actual actionable intelligence that works reliably in the real world.
Absolutely. So, thinking about that whole journey, here's a final thought for you, our listener. What new, maybe unexpected problems could you potentially solve if you embrace this full end-to-end process? Thinking beyond just the algorithm, from that initial spark of an idea, through the data wrangling, the modeling, all the way to a deployed, continuously learning system. You could even start exploring today. Pick a data set that interests you, maybe from a competition site like Kaggle.com, and just try to walk through these steps yourself. Frame the problem, explore the data, build a simple model, think about evaluation. It's definitely a challenging path, but as we've heard today, it's also an incredibly rewarding one.